All right, 1.3 linear equations that's the name of the game. Specific type of function. When we start kind of working with specific function types, it's usually a really good place to start. They're a little bit more basic. They're really important. There's a lot of situations they apply to in Precalc and calculus. They're versatile functions. They do a lot of things for us. Again, when you're starting to get into the details of how to work with specific functions, really, really good place to start. And that's what we'll do. Within that, as you're talking about lines, a great place to start is to talk about slope. You've probably seen this 100 times. I hope you have, right? There's some of those topics that I'm like, I don't know if I want to go over that. I think they're pretty good at it, and I think they've seen it all before. Slope, that's one of those where you've seen it 100 times. I hope you see it 100 times more. You can't see it enough. It's a hugely important topic. That's how it's calculated. If you want to put this on there. It measures a line's rate of change. That's what it does. It's a measurement. Some people think of it as it measures the line's steepness. It's a good way to think about it. Okay? When we're talking about slope, there's a couple of cases we could see. Slope can be positive. That means as your x variable is increasing, so is your y. And you would see a line that looks something like that. Slope can be negative, whereas x goes up, y goes down, and you see something like that. You can get a horizontal line where the slope is 0. It is neither increasing nor decreasing. Sometimes that's called a constant function. And if you have a vertical line straight up and down, that slope is undefined. Okay, and you'll see that come up in your homework assignment as to how that happens. I'm not going to show you right now. I want you to come across that case when you're kind of not expecting it to see what happens with the equation for slope. Slope-intercept form, again, this is probably something you've seen many times. Definitely our preferred form of writing a line. It's great for graphing. It's pretty intuitive, right? There's a lot of key components about the line, such as the slope and the y-intercept, which if we know those two things, that's enough to determine the unique line that we're working with. Okay, the slope by itself is not enough to do it, right? We have to also know where it crosses the y-axis, and that form tells us. All right. Got a couple, actually three equations here that I want to look at. Just to briefly talk about graphing, because on one hand, you could say after lesson 2, we don't have anything to talk about in terms of graphing. Didn't we look at putting together tables of solution points and then graphing those points? Would these lines be any different? And the answer, of course, is no. You could go about it and graph those that way. But one thing I do want to show you here is if you really kind of know your stuff with lines, I can kind of forego the process of making a table. I don't really need to do it. For example, on line number 1, it's in slope-intercept form, and I see its y-intercept is 1. And now I'm using the slope as I go up 2 over 1 to make all these other points. Now I could plug in these x values that I'm at and put together a table, but I just generated about 10 solution points in a fraction of the time. Okay? Start at a y-intercept of 1 and then use the fact that this number, 2, means as the y variable increases by 2, the x goes up by 1. So you saw to get all those other points, I went up 2 over 1, up 2 over 1. So I don't know. It's kind of up to you. Do you want to be safe and make a table and then plot those points? Sure. I wouldn't recommend using this kind of pattern for other function types because it doesn't work as well, but with lines, it tends to work fine. Right here at y equals 2, that's the one that has a slope of 0. Okay, if you wanted to think about it like this, you certainly could. That's why there's no x, is the number that goes with that x is the slope, and it's 0. Okay? You should notice something a little bit different about number 3. I would rearrange that immediately. Notice it's in what's called general form. X plus y is 2. Not a great form to graph, and I wanted for you to see that one because you could certainly come across one. You know, I would want you to recognize that number 3 is a linear equation. It's not really in the form we would want it to be in. But once I do that, I could go up to a y-intercept of 2, and now go down 1 and over 1, which is using the fact that the slope is negative 1. And again, I'm generating just tons and tons of solution points. We said from your table, you know, if you did 5 to 7 points, you'd have a pretty good looking graph. I think I just did 15. Okay. Now as far as calculating slope, I'll give you a bunch of them here. You need 2 points to calculate the slope. I'm not going to do all these just because I don't think we need to. It's the same calculation every time. Your homework assignment will give you plenty of practice at it, but that's a very important thing if you're just given 2 points, that you could plot them, connect them with a line, and then you could calculate what the slope is in between them. But I would have all these written in your notes just because, come review time for the test, it's always nice to have a few extra examples that we can come back to, particularly for topics that are important, like calculating slope. Oh, I'll just do the first set here. Here's negative 2, 0. And there's the 0.31. They're not very far apart. There's the line in between them. Looks to be a positive slope. I'll take the difference in the x-coordinates. That would be 1 minus 0. And then I would do the difference in the x-coordinates on the bottom, because it's change in y over change in x. That would simplify to 1. The bottom would simplify to 5. I have a slope of 1/5. And again, that means for every 1 unit the y variable went up, the x went up 5. Okay? It's positive slope. It's not very steep, right? We could say that for this particular line, perhaps that it's not increasing all that quickly, to be honest. It's not a real steep slope. All right, now I want to talk about writing equations And I'm going to kind of steal a little something from our slope definition, except I'm going to change one thing up a little bit. One of those things that seems really small, but it's actually not. It's kind of a big thing. I took the x2 and the y2 out, so I'm now saying I don't have a second point. I just have the 1, x1, y1. But I'm now going to assume that I have the slope. I'm going to rearrange this. I'm going to multiply both sides by that denominator, which would leave me with this. Okay? What you have here is point slope form. A lot of times in the context of like a word problem, we might have an idea of what the slope is and maybe one point that's on it. And if that's the case, this is a great, as far as making the jump to an equation, this is the form to use. So again, m is your slope, and then we do have to know one point on that line. But I wanted you to see that that equation is really nothing more than just the definition of slope kind of rearranged, and it gives us a pretty useful form of a linear equation. All right, I'm going to give you a couple definitions here just in simple terms. You'll notice I do that all the time. If you want a really technical definition about this stuff, go check your book. It's got the really technical language, and those are fine, and some of you may want those, but the definitions I give you in your notes from these lessons tend to be in just really simple terms. Okay? For example, if two lines are parallel, they have the same slope. You should equate those two things. If you see those slopes are the same, that's what's going on. Perpendicular is a little bit more complicated. Okay? The relationship is that the slopes have a negative reciprocal, and this is one I'm really not that concerned about how you would define it, because the definition can get kind of wordy. This is one where I'm concerned that you know it when you see it. For example, let's say your first line has a slope of 3/2. What would your second slope have to be for you to have a line that's perpendicular? And that would be -2/3. And I find that most pre-calc students know it when they see it. It's like a fraction. It flips and the sign changes, and that's really what you need to know. Okay? All right, down here what I want to do is use this point slope form a couple of times to get two lines here. Because I know a couple things about the lines I'm going to find. I know these two lines I'm going to find have to go through the point 2, -1, but I've got this other line right here. Notice it's not in slope-intercept form. I don't really like that, so I'm going to switch it. But these two lines, the first one's going to be parallel to the line that I was given, and the second one's going to be perpendicular to it. Okay? Now, when you see this, you should think immediately, we should go right here and say -3y equals 5 minus 2x, and then I would have y equals -5/3 plus 2/3 x. So that's the line that was given, but now I have it in slope-intercept form, which again I like because it's easier to see. This has a slope of 2/3. Okay? So now here's what happens. This is where point slope form becomes really, really useful. Okay? According to that definition, I could do y minus a y coordinate of a point that I was given, which I have, -1. Now this line has to be parallel to the one that I was given, so it's going to have the same slope of 2/3. And x minus 2. Okay? Notice all I have is an x and all I have is a y. And as far as getting the equation, that'll work. Okay? I have to rearrange this a little bit. This would become y plus 1. Should distribute my 2/3. I'd get minus 4/3, and then I would subtract 1. That's not going to do anything to the slope. That should be 2/3 just as it is. Oh, when I subtract 1, I'm really taking away 3/3, so this would be minus 7/3. Okay? Now over here, I want you to see how similar this is going to be, because this line still has to go through the same point. The only difference now is this line needs to be perpendicular to the one that I was given. So in this whole process, all that changes is that becomes -3/2. And I'm still going to have x minus 2 because this line is also going through that same point. Steps to simplify are identical. When I distribute here, I actually end up getting plus 3, and then when I subtract that 1, I actually don't have any fractions to deal with. I get -2/3 x plus 2. Okay? Notice both of those lines finished in slope-intercept form. If you get a problem like that, your answer should, right? Technically, we have the equation right at the beginning when we were in point-slope form. That's a lousy form to leave your answer, though. Slope-intercept form is much better. All right, a few application problems to just take a peek at. Using slope as a ratio. Okay, I've got this diagram of a ramp. And what I want to see here is, does it fit the recommendation that the steepness should be no more than 1/12? Okay? No more than 1/12. Now the first thing I'm going to do here is look right at that. Okay? I got a little unit situation going on. The two units don't match. The rise of that slope is in inches, and the run, that's a term for the change in x, is in feet, which is not good. I'd want them to be the same. Okay? So now what I'm going to start with is looking at this recommendation. And 1/12 is this approximately 0.083. Okay? The steepness should be no more than that. So that's really what I'm now checking. As I can see for the ramp that we have, it increases 22 inches as it horizontally goes 288. Comparing these numerical values is better as decimals. It's a comparison between these two slopes. We don't want it to be any steeper than 0.083. 0.0764 is less than 0.083. So to answer their question, is the ramp steeper than recommended? No, it's not. It's less steep than recommended, which is good. It would fit the recommendation that was given. You'll see problems like these come up where you have to do some interpretation. Okay, this is a linear example that's modeling cost of, I hope that you see in these problems that the context is kind of irrelevant. It can represent anything, right? This one's about a company that manufactures kitchen appliances, and they're talking about the blenders they produce, okay, and how much it costs to do so. Pretty typical business example. But when I said the context is irrelevant, the context could apply to anything, right? That's the beauty of these types of functions, is they can be used in so many different situations, all right? Your y-intercept is right here. Now, really what I want you to think hard about is x is always 0 at the y-intercept. Okay, so this 3,500, it's a y value, so it represents cost. But specifically, it's the cost when no blenders are being produced. Probably the most succinct way to describe it. It's your fixed cost. Okay, this company is going to take on $3,500 of expenses, even if they aren't producing a single blender. Okay. Now when we look at slope, right, that is change in y, which is $25, over x, which is in blenders. There's more cost associated with producing the blenders. That slope is telling you a really relevant piece of information. It's the price of making one, right? We've got those $3,500 of fixed costs that we'll have, but then as we start producing blenders, it costs $25 to make one of them, right? $50 to make two of them, $75 to make three. That's why you see this positive slope, and you see it start to increase. These last two examples involve writing equations, okay? So what we'd be after here is to get an answer in the form of y equals mx plus b. Okay? So I need a slope and I need a y-intercept. Okay? And again, the big thing with the y-intercept is it happens when x is 0. Okay? I'm going to say that x is time in years after purchase. So if I want my y-intercept for b, within the context, I now need to be thinking, what did this equipment cost when it was new? Okay, after no time had gone by. And fortunately, that information is just given to us. Okay? It's $1,200, and it's clear from the problem that the value starts to go down. It's a matter of how much, right? Y is going to be in dollars. That's the value of the equipment. So the next question becomes, do they give us enough information in this problem to figure out how much it was going down? Because that's what I need for the slope. The answer is yes. We have 2 points, right? Really what this is telling us is that this line includes the point 0, 12,000, and it includes the point 8, 2,000. Okay, now we've already talked about right here, this 12,000, that's going to be the value of B. Okay, but now I do my change in Y, that we went from, see if I did 12,000 minus 2,000. Then on the bottom I would have to put 0 minus 8, which would be 10,000 over negative 8, which would be negative 1250, and that would tell you on average how much value we were losing per year. So to put it all together, I'd have Y, which I already defined, that's in money, that's the value of the equipment, was 12,000. But then I have to take away 1250 x, and that is what you'd be looking for, right there. Here's another one that's looking at the change in Starbucks shares from a few years ago. I had looked it up recently. I think Starbucks shares are more like $70 now, so they've gone up quite a bit since 2002 and 2001. But again, the very first thing I want to do is define my variables. X is years after 2000. and y is in dollars, and that's the price per share. Sometimes this step gets overlooked, and I find that students don't do it. It's hugely important before you start to write a model. What is what, right? Keeping the x and the y variable straight is really important, and that's why it's where you want to start. What is x? What is y? It's worth putting a little thought into that to make sure you're clear before you proceed. Okay. Same deal. This one didn't just give me the y-intercept like the other, but what I do have is enough to get slope. Because again, I've got 2 points. This is telling me in 2001 the price was $6.97, and then in 2002 it was valued at $8.47. Change in y over change in x. This comes out to be 1.5 over 1. Or just 1.5, which tells me that the price is increasing $1.50 per year. Okay? Increasing $1.50 per year. Now, here's the deal. This is that case that I was telling you about where we can go to point-slope form. Okay? I could say, because I still don't have the y-intercept. This was a big first step in getting this equation, but I don't have b. Okay? But I can use one of my points, and it actually doesn't matter which one you use. That's the beauty of point-slope form. There's y minus a y value. There is the slope, and there's x minus an x value. Okay, I just need one. It's starting to look like that problem that we did a couple of slides ago. Because at this point, all I really need to do is get things rearranged. So I get to slope-intercept form. The 1.5 needs to be distributed, and that'll look like that. And now if I add 6.97, I'll still just have 1.5x, but I will get 5.47. Okay, that line relates years after 2000 to the Starbucks price of essentially their stock value is what the problem is referring to. Now you could check it. If you plug in 1, do you get 6.97? If you plug in 2, do you get 8.47? And now the last part, which I'll leave up to you. We want to use it to predict the price in 2003. Plug in 3, right? What happens when x is 3? All right. It's positive slope. Price is going up. About $1.50 a year, but if you plug in 3, you'd get the prediction for 03. I'll leave that up to you. If you want to check that answer in class, feel free. But that is all for 1.3.